Alright, so I think we're good to start. Hey everyone, my name is Jinen. Today we're going to be talking about mechanistic interpretability. It is a very interesting concept. We'll discuss about what interpretability is, what mechanistic interpretability is, and everything in between. So if you are a bit out of the loop, that's fine, do not worry about it. But importantly, please ask me many questions, completely bombard me with questions. That is exactly what I need, because that's the way I'm going to understand if everything makes sense or not. These are the two papers that we're covering, circuit analysis and monosemanticity. So the links for those two are there. I also included the slides in the Discord channel, so you can check that out if you'd like to follow along. Most importantly, also, this is just my understanding of it. So some things might make sense, most things might not, and let me know when we come across those most things. So cool, let's get started. This is the three basic outline of the presentation. We'll talk about the background, intuition, why this is an interesting topic and why you should enjoy this, circuit analysis, and monosemanticity. But the overview basically is we're trying to understand why attention works the way it does. We have our sort of intuitive basis that we use in order to sort of set up an analysis, but that does not actually relate to how the transformer architecture actually learns when we sort of backpropagate through an input. And the objective with this is to just study that and gain a more mathematical intuition for why attention works, and not just the fact that it's a database and that somehow seems to figure itself out during gradient descent. So background and intuition, what is interpretability? And I think my favorite introduction to that is this. It's XKCD 1838. There's a person saying this is your machine learning system on the side, and there is a man on the pile of linear algebra going, yes, you put the data into that funnel, and you get an answer on the other side. If the answer is incorrect, you just keep mixing the variables until it starts to make sense, and once it starts to make sense, you've kind of got your model, right? And this is where most people stop. They find a model that makes sense, it gives them answers that look nice and have a high accuracy. However, the problem is that most of these models sort of have or function on certain underlying assumptions, which may or may not be apparent that they are broken just with a high test accuracy. So interpretability seeks to understand why a model makes the decision it says it does, and the cause for whatever decision, and basically kind of inception. If we are able to predict what a model is going to predict, that is how we know we have an interpretable model. So even if the answer is incorrect, we should be able to predict that fact that it is going to get us an incorrect answer, and that's when we know we have a model that is interpretable. Now this is easy for something like shallow learning, right? So if I give you a cluster and I say we are using TNNs for this, I give you a point, and you can manually compute what the point is going to be, right? You can manually figure out that prediction. You don't need a computer to figure that out, as long as I tell you what k is, right? Similarly, for decision trees, it may be obvious what the splits are, but again, even that gets very complicated very quickly when we sort of exceed the base dimension, or like we exceed shallow trees and start getting into trees that have very high depth. Anyways, for deep learning, this generally is automatically significantly harder, because you cannot really pull out a neuron and say this neuron's weight is 5, which means that it should have certain types of behavior. And this paper, or this set of papers basically comes or makes an attempt to challenge that exact problem, right? So we will interpret deep neural networks, which is generally very challenging. So this is going to be very interesting. The way we start off interpreting models mostly relies on an architecture that's very simple, a toy model. And the reason we use toy models is we can generally figure out what the computation for a certain hidden layer is going to be just using a paper and a pen. And that's important because that means it gives us a very solid ground truth to compare against. So if something doesn't make sense, we can figure out exactly the fact that it's not making sense. We can say that there's something wrong over here because we expect X but we are getting Y. Generally we can't do that because we don't have an expected set of optimal parameters, but a toy model gives us something that we can analytically say this is the correct answer, right? So for mathematical simplicity, we are going to use a toy model. This toy model ignores biases. You can assume a bias is part of the weight matrix. That will kind of solve the problem. We are not using layer norm, and we are not using dense layers at all. So generally, if you look at the normal attention or the normal transformer architecture, the multi-headed attention is what is described over here, sort of in this section. I'm highlighting it with my mouse, but if it's not obvious, let me know. And then after this, we have a multi-layer perceptron, layer normalization, as well as multi-layer perceptron. Then this goes to the decoder or the following for the following head, right? We are skipping that. This allows us to do the math a little bit more easily, and then afterwards we will remove the last assumption and actually include a MRP as well. Why this is useful, I kind of alluded to this. We will be able to understand after this bit why attention works and observe recurring patterns in complex models that actually sort of extend towards your practical use cases. Cool. Actually, so far, do we have any questions? Does everything make sense, or does something not make sense? Yes.
Even though differences of a bias layer norms and dense layers, don't they do?
Sorry, could you repeat that question?
Biases, layer norms, and dense layers, and like what every single one does.
Yeah. So we have for a normal dense layer, right? Let's say we have 1 and 2 features over here. I'm trying to draw a neural network. It's going to look messy very quickly, so I'll keep it small, right? We go 1, 2, and 3 over. Oops, 1, 2, and 3 over here, and then 1, 2, and then 3 over here. So this is like a single feed forward layer, correct? These are 2 features that we have. Let's call it x1 and x2, right? We need to, in addition to just this feed forward layer, we need to add an additional input. This additional input over here is your bias, and then this sort of extends to all of the 3 as well, right? And this thing is something that we are just generally ignoring. The reason it is important, we can very easily describe just with a normal linear layer, or like a normal linear classifier. So if we have a line, we want to demonstrate it with y equals mx plus b, right? That's the formula. So I can demonstrate any line in a 2D plane with those 2 numbers, m and b. M is this line over here, and then b is the height of 0. So if suppose this is 1, this region over here is 1, that's how I know that this is what your bias is basically, and your slope can be, I don't know, it's 2, then m is equal to 2, so m equals 2. So that's why the bias is important. Layer normalization, we have layer, let's say I add another layer over here. I'm not going to draw it out, but we have one layer over here. The weights for each of the each layer is, no wait, that's not right. For multi-headed attention, we have multiple heads, right, that sort of accumulate together in the class. So what layer normalization is doing, it is just ensuring that the weights for all of these layers are within a certain range, and what that allows us to do is ensure that the gradients don't explode or implode. So it just is to ensure that backpropagation doesn't go crazy, where one layer is training in some other direction with significantly higher weights, the other one is significantly lower weights. The model gets confused and learns nothing at the end. Again, this is just empirically what works. There is some theory behind it that I'm not able to write out right now because I don't know it, but I can probably link for that later. So that answers the question. Did I miss one thing? Dense layers is just MLP, so this is just a dense layer. Awesome. Cool. Let's talk about mechanistic interpretability. Generally, what interpretability tends to achieve or aims to achieve is this kind of output where you extract some information from either the parameters, the outputs, or both of them in order to get a representation of the input that gives you some idea of what's going on. So for this case, I have a normal classifier model and a CNN. what the CNN or what this is doing is it is showing us the activation map, so a basic heat map over the original image, where any weight that is in red is a higher weight, and the higher weight means that it is focusing more, or it is contributing to the prediction more than the blue region. So we're doing that for these 4 images, and it's a very high layer of granularity because we are understanding the model up to a pretty high depth only, right? Mechanistic interpretability goes a step lower, or in fact multiple steps lower. So it places an emphasis on reverse engineering neural networks, where we take this series of weights and say we are going to figure out what every single weight does. And the benefit of understanding the functions that every single neuron plays within the inference means that we can offer high-level explanations for decisions. This is similar to the thing that we have up top. But in addition to that, we can also ensure guarantees for certain behaviors. So one thing that's really cool, which we'll discuss in a bit, is that ensuring or having this level of interpretability for a type of model will allow us to get or restrict sampling of the generation model to only show Arabic or only show HTML based on a single setting that we change, right? And the weights themselves are effectively exactly the same. So that is our background. Now we're going to talk about circuit analysis with the transformer architecture. So standard n-gram models, right? We are predating transformers here. Use the following assumption in order to sort of build a generalization for their approach. They basically say that we have x of t, which is x of t, which is the new token that we are looking to predict. This token prediction is dependent on all of the previous tokens before it, right? This is true. So if I say this is a cat and I remove the word cat, your prediction of your next word depends on all of the words before it, right? If you are reading it, if you are reading a sentence as an example. But in truth, you don't really do this. If you are reading a book, for instance, and you are asked a question halfway through the book, you will not basically consider every single word that was said before it. You will consider an abstraction of it and really only focus on maybe the last 2 paragraphs or something, right? So that's their intuition, where they're saying that the entire thing can be approximated by only using the last token and not the entire set of tokens before that. Now this holds true empirically for us if we are talking about models that are, if we're talking about answers to a comprehension question, because we can read 2 paragraphs. But for a computer to read 2 paragraphs is also incredibly large, right? The models that we usually use are like bigram models that produce very usable explanations of our text. So what we end up doing is this kind of sad approximation that doesn't really work and gives us a lot of incorrect answers, which is a bit of the motivation for using attention, because context is important, right? Context is important. That's why we can't just use the last token. We try to use more than the last token, but the extent that we can do it while staying computationally efficient is very low. So efficiency is also very important, right, as we discussed. So one solution that we came up with was the transformer. We say we'll give you a much larger context, but don't compute all of it. Just tell me which parts are important, and I will compute those specific parts only. And in our construction of the transformer, we have the attention heads, right? Self-attention heads. This is something that we discussed last week when Alexei gave the presentation. But but it is kind of pivotal to our conversation here. So I have just like a one-slide summary of self-attention specifically, right? We have our query and key vectors, which we compute against each other, and we normalize that, run it against softmax. Once we run it against softmax, we run it against our value vector and get the output of our attention. Is that a hand raise?
How is it more efficient to train the database?
So the self-attention effectively is like establishing a database. We create a map of keys and value pairs.
So is it because you're only training on the embeds instead of training on every possible word?
We train on every possible word, every word in the vocabulary. Yeah, we do train on every word in the vocabulary.
Then how is it
Vocabulary.
more efficient to train the entire?
Because you learn like what to look into, right? So like the whole point of like the keyword
Oh.
value.
So,
Yeah, that's what
sorry,
you do.
I'll be more clear. So the idea is, so most transformer architectures use a vocabulary of 36,000 words, 36,000 tokens, right? Maybe I'm wrong, but that's approximately it, right? We create this database of what these words mean, which is an embedding, right? We generate that and add positional information, then we run it through self-attention. Self-attention's purpose is to identify which words are important to subset the computation to only those tokens. So if I have a whole book, right, there is a infinite transformer, which is or infinite attention, which is a transformer paper that basically extends attention to an infinite context. What that effectively does is it extends the theoretical model that we are discussing right now and performs the attention or like the computation of attention on that entire set. So it allows us to represent the most relevant information in the same vector space. That's why it is better than using the n-grams. So for instance, let's use a sentence, the man said, and then over here you have a very long sentence, okay? Now I will complete the sentence and ask you a question, who said this, right? And your answer is man, correct? However, in order for this word man to become part of your context window, you would have to have the number, you would have to have an n-gram where n is larger than this entire sentence plus these two. So man has to appear within the context window for it to be represented, and doing that one is very computationally expensive the longer our length gets. So the transformer reduces that major thing and also allows it to be represented in a smaller amount of space. So let's say each token is represented in 768 tokens, and this sentence has length 5, right? I will have 5 plus 6, 7. 7 gram is going to be able to get this in, but it will also have to compress 768 times 7 into maybe 512, right? Which is a much bigger ask. Attention does that same thing much more efficiently because it conditionally figures out based on the query what set of words should be important, right?
I see.
Make sense or not 100%?
Not 100% yet, but I think that I'll research it more.
Okay. Yes.
What's an n-gram model?
So an n-gram model, n basically just stands for the number of words in context. So if I have a sentence with the 10 words, I have when each word is a token, I'm changing it, it's 4 words. So an n-gram model where n equals 2, for instance, will take the last 2 tokens in order to perform the computation. And or like the neural network takes the last two tokens as input, and then it processes an output y, right? And that will be a new token, for example. So if I was to so now technically n-grams are not even neural networks, it's almost like a conditional prediction. So say I have a database and the frequency of words in a particular database. I say, given the password is hello, what should the next word be, right? And this prediction becomes over here world, right? And then when we increase the context, so this is a one gram model, and the more we increase it, our context window, the more words we have inside that period. So we are conditionally querying on a sequence of tokens rather than just one token, which makes the answer more correct. Okay, and this is pretty foundational for a lot of NLP things, and it's also kind of basically this input that RNNs use to a certain extent, where they take the last few set of text, run it through their recursive model, and then the gradient is displayed for those recursively computed like latent vectors. So you would convert this thing into into a neural network, or use a neural network to convert this to a different tensor, and then add the tensors for these two, and then use that in order to generate your final output. So what ends up happening is that over time, the first few values, right, they kind of disappear. So that's the problem with the RNN as well, where the gradients kind of go away. So it behaves like an n-gram when we are considering a sentence like this, because the RNN only has tokens, say, up to 4 words behind as gradients. So does that answer the question?
So we can break down a bunch of tokens to less tokens by grouping them together into like n-grams.
You can, it's not really grouping them, it's trying to take the conditional probability of 2 independent events. So let's say I have A1 equals hello, and then the A2 equals world. So you're basically computing A1 times A2, and the probability of word X given A1, A2. And X is your entire you basically X cycles through your entire vocabulary. So let's say I have 3 words. I don't know. Give me 3 random words. Dog, cat, apple. Okay. I predict probability of dog given hello world, cat given hello world, apple given hello world. Now none of these 3 words make a lot of sense, but one will have a higher probability than the other. We just extract the one that has the highest probability. That's how the n-gram will predict a new token. Then we take X and predict another one by saying Py given, let's say this is world and this is this is hello and this is world. So hello and world, homework, and we condition this on A2 and then X. So sorry, this is not good representation, but we basically get our new token this way, and then we can keep on recursively or auto-regressively sampling this n-gram model or bigram model to get our prediction. Awesome. So one more question, yeah.
I just wanted to clarify if I'm understanding this correctly, the self-potentials
Yes.
synopsis. So there's this raw database, and we have another process that determines the subset of important tokens, and then you feed it to the deep learning model.
Yes, exactly. So the alpha I is the attention for a specific token, and it is basically a probability distribution over the sequence of words, and the sequence of words that has the highest probability will be reflected in by the attention, and then we basically pick out whichever, or we multiply this by a value vector, and the value vector is the word from the database itself in the vector form, and that's the final output representation, right? So that's our, yeah.
Just confirming, do we take some k amount of words that was important, that's consistent across every time we run the model, or does it have a certain cutoff in terms of how the probability looks like?
So softmax by itself is super huge. Like we run softmax on the final distribution over the entire vocabulary. So theoretically, the maximum for softmax is very, very high. However, for this, we basically it's empirically determined. So you can have a context length of 10 or 20, something like that. Some have much larger context lengths. But the important takeaway is that it is much more significant than what an n-gram model or an RNN is capable of doing. Cool. One more question there. No. Okay, and that is a fantastic question. So the keyword over here is trainable database, right? So we create this sort of database setup and tell the model, now you figure out what this database is supposed to look like. You figure out what the key vector, or the weight matrices for the key vector, the value vector, and the query vector is supposed to look like. Okay, and your challenge is to identify what makes sense and what does not make sense. And gradient descent somehow manages to do a fantastic job at this. Okay, but intuitively it makes sense because our intuition is that we are asking it to create a database and it creates a database successfully. But internally, this is not what happens. Okay, so is everyone clear on self-attention before we move on? Because understanding this is important for the next slide especially. Make sense? All right. Okay. So now we want to reframe this operation. We want to reframe self-attention, and we want to reframe our entire method of looking at the transformer model. So very quickly, if we have a standard MLP, one way to look at this. Why is the contrast blown? Okay. One way to look at this is we have a weight matrix, right, times X plus a bias. And then we run this through an activation. Usually this is a ReLU, right? Nonlinear activation. So this is an example of a single hidden layer, right? Demonstrated mathematically. So this thing can be used recursively. So I can specify a new layer Z that takes W, Y plus B, and then does this exact same process. And then I can feed Y over here to create this sort of very big equation. Okay, so if I have a very long model like ResNet, theoretically I can create Z as a function of X that basically cycles through all of the layers to generate us a final output. We can do the same thing for this small network, but doing so does not give us a value that makes a lot of sense because we can't really do much with it. It looks very complicated, and that's not good, right? It may look cool, but at the end of the day, we want something to be simple for us to be able to interpret it well. But representing attention using tensor products kind of allows us to do that, right? So what's happening over here is we are taking the value matrix, the output matrix, as well as A. This represents attention, and creating this sort of pattern, right? For vector operations, we go from right to left, which is how I would like you all to also process this. So we have our input token that is after the embedding stage over here is X. We multiply it by I times V. So I is the identity matrix. It is a tensor operation against the value vector matrix. Then you process attention. And attention is there in front in the first space. That is because you are dividing attention across the identity matrix versus I product or like I tensor product WV, which is more like batch evaluation, where you are evaluating the same WV against all of X. So we have that, and then finally WO as well, W sub O, which is for the exact same process as W sub V. And that gives us our output, right? This is not very exciting until we realize the fact that we can sort of compress that top line of the equation down to this bottom line or equation 5, where all of the equations on one side basically just merge, okay? So even though we are computing WO after A, we can merge it into the same space as WV. The only thing we need to remember is that the order of operations within that space should make sense. So we have this sort of shorthand for the hidden space. Now this basically means that attention and the weight matrices are disjointed in some sense. Question?
Just to clarify, what is WO and WV?
WO is the output weight or like output parameter metric, output parameter matrix, and WV is the value parameter metric. So going back to the attention slide, attention slide, we have softmax. Good point actually. I did not include W or like O. So we have the Q, K, and V, and these are independent parameter matrices. O sub I is another independent parameter matrix that is computed after H of X. So you compute H of X against the value, and then after the full all of the attention heads are computed and merge into one, you run it against another output matrix, or output parameter matrix. And by parameter matrix I mean it is trained, so the weights of it we randomize, initialize it randomly, and then let backpropagation figure it out.
Is that the factor by 5 matrix?
Yes. Okay, does that make sense?
Yeah.
Fantastic. Okay, so we can question.
Another question.
Yes.
How do you know that the operations are commutable? How do you know that you can I cross W0 then next slide. How do you know that you can like basically
Merge them?
How do you know you can like swap the W0 and A in this case?
You cannot swap. Oh, you can't swap W0 and A. You can merge everything on one side.
Oh,
So,
okay.
so everything on the right side gets merged into the right
W0,
part, and then
okay,
everything on the
sorry.
left gets merged into the left, and then
Makes
all
sense.
of the identities we can ignore. Okay, cool.
Where does your I go?
It's I is identity. So identity times the matrix is the matrix itself. So we can just ignore
Oh,
those on
okay.
the left. Right? But when they are by themselves, obviously we have to include.
I wasn't sure what.
No, thank you for asking. Please keep the questions coming. Okay, so we have the hidden output, and the key takeaway over here is that the attention is independent of W sub O and W sub V, and this tells us a lot. So first, they are fundamentally independent, not just in terms of their function, because obviously they do interact in the future, but in terms of their learning. The way that the parameters are optimized are inherently different. Even though it is under the same backpropagation step, they almost kind of learn separately. So A or attention describes what which token information. Oh yeah, okay. So the way that we want to look at this is through that original diagram. So I will very quickly just draw that here. So I have my input, which is, what is it, T0, which is the token. I want to generate the next one. I will compute this through W sub of E. This is our embedding parameters, like embedding matrix. This gives us X sub 0, and from here we can compute this against attention, right? Am I getting the diagram wrong? Yeah, no, this should separate over here. I think I messed up. Give me a second. Yeah, it should. So this, ignore very quickly, and it separates up into all of the very many heads, and each of these heads independently carry out the operation of attention, and then there is this residual layer that merges into all of this with a plus 1, 2, and 3 over here, and from this you go back to the unembedding space. Yeah, okay, cool. This is W sub U for unembedding, and I'm going to name this X1, and this becomes our Y. Okay, so this is kind of the model that I would like here to contextualize as we process how H works. So H over here is this function, this thing over here. Cool. So now the attention matrix effectively tells us what set of token information moves through from X0 to X1. So this step has a lot of transformation of data present within it, and the attention basically tells us which ones to look at, which ones to focus on, which set of matrices actually move through up to X1 and which ones are lost to the void. And W sub 0 and W sub 1 is the transformation of X0 into X1, and that basically tells us how the value vectors effectively evaluate the data. Since the embeddings that we get over here only have positional embedding, which our toy model does not even have, but I mean, WE can be abstract. You can assume that for it also manages to encode position perfectly. But the general idea is that W sub O, W sub V is the transformation of X0 into X1, and attention is only attention clarifies a subset of that to sort of compress into the same dimension, into the same dimensionality. Okay. So our multi-headed attention formula, right? So H of X is just for a single head. We still have to accumulate this. It looks like this, where we have X sub 0 over here that we are adding it to all of the attention heads. So we're just going through all of them, computing the specific formula for every single weight matrix, because the weight matrix is different for every single attention head. They attend to different things. For our example, I think we have the model that we're using has 12 attention heads. Cool. So our final transformer now has this equation. We have the unembedding matrix, again tensorize against identity, and then multi-headed attention 1 times WE, and all of this is times TO, which is our initial token. Cool. The last parenthesis should not exist, right? Yes, the last parenthesis shouldn't. No, wait, it should. Yeah, no, this makes sense. This makes perfect sense. My bad. Equation makes sense. Okay, so far does this bit make sense? Are there questions for me for this slide specifically? Yes.
Where did WU come from?
WU is unembedding. So we have this over here. So since we are focusing only on attention head, WE and WU don't show up until the last slide, but the WO, WV do, and then we also have WQ and WV. WQ and WK, which is query and key. Those will show up in a second. Cool.
I'm still a bit confused about where you got that equation 4 from, like where identity comes from, and you can say that they're fundamentally independent. They're both, like during training, they're both very correlational. They get the same inputs to then train themselves on with outputs.
So if we use equation 5, right? Let's just we take these in order. So first thing was question 4, for equation 4, where we are converting. I should have a shortcut to move slides. Okay. Anyways, we have this hidden equation, and we are transforming that into this. That part was not clear.
Well, what is I?
What is I? I is the identity matrix. So we are. It's just a matrix we are representing this exact same equation. Nothing is changing in the results over here. It's just reframing the equation, and it's what we we learn this style, correct? Because we are these two equations, right? You can merge the a sub I into one to create that. But it's basically the equation 3 is just attention head, right? A single attention head.
That would get you a matrix.
Yeah, and I all the way to t is all of the tokens. So if we are generating, we have x sub t. We have if we have x sub t plus 1, we will have I through t tokens, which we are comparing against, right? In the theoretical case where we have full maximum context or infinite context. So we have that, and then this is just converted into the tensor form. Yes.
Why do you even need that I in the first place? Because like from my understanding, it's just I cross over 0, isn't that just W0?
It's like unsqueeze in PyTorch. You are adding 1 comma to the.
Oh, okay.
Well, I'm not saying in actual matrix form, because if you do identity cover.
Oh, okay. Yes, that makes sense. Okay.
I'm saying internally, the easiest way to process it is that it is unsqueezing the first dimension.
You're just like, I don't think I should mention basically.
Yeah, exactly. That's exactly it. Okay, sweet. Okay, was that clear?
I think so.
It's not clear, I don't mind repeating anything.
I'll have to go through it later again.
Okay, I mean, does anyone else have questions? What part of this does not make sense? Please ask. Yes.
So just to make sure, the identity matrix is the h of x function from the previous slide, which includes the attention, or is the identity just attention?
Identity matrix is just this, right? It's just for instance, for 2 by 2, the identity matrix is just the one along the diagonal. So that's basically what we are doing against A, B, C, and D. This is the operation sort of unpacked if we were to look at it individually. And this I over here, for instance, if we were cycling through it, you would have I equals 1, 2, 3, 4. This is probably not an exact comparison, but if you were to sort of visualize what is happening or what we are doing, right, is we are removing the summation and putting it in tensor form, and that's what the packing operation is basically doing. Right? Does this make sense?
Yeah, no, I was just making sure because when you were talking, I got a little confused about what you meant by identity matrix.
Okay.
You were talking about softmax and the attention.
Right.
I got a little confused. That makes sense.
Sorry. Okay. Now it makes sense.
Yeah.
Fantastic. Okay, cool. Disjointed nature tells us a lot. They're fundamentally different in the way they learn. That's important to note. Our finite transformer has this following equation, and we need to understand why this is so important. It is interesting for reasons A and B, but why is it so important? We can first simplify to just T, so remove some, like abstract out the T0, we just don't ignore that. And then sort of expand multi-headed attention to the formula that we have identified previously, and then get the tensor as this sort of breakdown. Okay, and we have W sub U, W sub V. This is our residual layer. So this line is basically W sub U, W sub V, and all of the individual heads are computed through that equation, where every matrix is different for the head for O, V, and attention. So we have this simplification. And this is interesting because we are able to actually make inferences on the nature of the input, we are able to make inferences on how the input is processed, right? So each thing represents something. Question?
Yeah, good question. Why do we have to multiply the identities? Like, I get like the summation of like multi-heads. Why do you need the I cross WE? And then you add the addition of the multi-heads. So like in line number 9, you have the I cross WE plus, and then the next term after that, I get that's the multi-head attention. What's the point of the I cross WE before it? If you know what I'm looking at?
Oh yes, that's that is x sub 0.
Oh, is that the bias?
Yeah, that's x sub 0. So I times I cross WE is x sub 0. So it's the residual correction over here, and then that is being processed after that. Yeah. Okay. And we multiply this by the unembedding layer, and that's how it sort of comes out and gets unpacked nicely into that final W sub U, W sub E. So we have that, and then the second pair, right? Both of them have W sub U, W sub E, and W sub O, V, and A is just for the. Oh yeah.
Yeah, I may have just missed it. What was the superscript H? Is that just the H of X?
Superscript H is for the hidden layer. So for instance, over here we have like multiple hidden layers, right? So 1, 2, 3, 4. We have 4 hidden layers over here. And all of these 4 hidden layers have their own sets of weight matrices. So the values for the weight matrices are different, even though the dimension is exactly the same. So we are basically going through computing the response of the result from each of the individual attention heads plus the residual, and then combining that into one equation or one matrix, and that's the output latent layer.
And the weights were from the H of X,
Or
where were the weights from?
the weights are randomly initialized and then trained using backpropagation. So you just randomly spawn weights with very small standard deviation. So you sample from a normal distribution with very small standard deviation and mean 0, and then automatically it will train and identify weights that make sense. Okay. Now the function of each of these individual things. Okay. Also, I realize it's 8:53 and we're like not even halfway through. Okay.
You want like split up into 2 sections?
Probably we'll do that, yes, because I don't want to keep you out here all night. So yeah, I will try to complete. So there's technically 2 papers here. So I will complete the first one, and then we can do the second one next week. And sorry about that. Okay, so W sub U, W sub V approximate bigram statistics. So our n-gram model with n equals 2 is basically what W sub U, W sub E does, and H dictates what the attention heads attend to, what tokens the attention heads attend to, and then this entire bigger chunk below that describes the behavior of logits if we attend to a given token. So it's basically the more expanded version of what we discussed over here.
What are logits again?
This token information moves through and residual subspace. Logits are just the, if I compute softmax on the final layer, the values I get are logits. Okay, I went too far ahead. Right, so this entire thing describes the behavior of logits if we attend to a given token. Now, an interesting observation here is that this equation is actually linear if we fix the attention patterns. So if we try to sort of look at this breakdown, we see that the only non-linear operation is softmax that is computed within the attention head. That's the only non-linear operation that we're carrying out here. So if we fix the attention pattern, if we basically give it a fixed matrix, it is going to be, this entire equation is going to be linear, and this means that we can perform an additional set of inferences based on that assumption. Finally, let's also unpack the last thing, which is the attention head in tensor product form. Okay, so we have Q sub I and K sub I. We can represent them using the equations W sub Q W sub E and W sub K W sub E times T0, which is our token, right? Question?
I'm so sorry, but what is a tensor product?
Tensor product is very good question. It's kind of matrix multiplication you're familiar with, right? It's just matrix multiplication with more than 2 dimensions. So there is no, I don't know how to describe this. Does anyone know how to describe tensor product better than me? Can you please try?
Multi-dimensional matrix multiplication.
Yeah, but if you didn't know what tensor product already was, would that help you though?
No.
Yeah.
It's like, just think matrix multiplication, but in 3D. It's like going from 3D to 4D. It's just there. It's just there.
There is like an awesome video on tensors and tensor multiplication on YouTube, and I will find that and send that on the reading group.
One Brown also has a good video.
Yes. Okay.
Thank you.
Cool. Sorry, I'm not able to answer that very well, but 3D matmul is the best approximation, I guess. Cool. So we have Q sub I, K sub I times our original one-hot encoded tokens. We then apply them to unnormalized attention. So we remove that square root of T sub K just in order to simplify this process. Question?
Again, for tensor product form, is it dimension in the same as the dimensions out? For like the input and output?
For dimensions in same as the dimensions out? No, not necessarily. For our case though, one very interesting property is that the dimensions are the same, which you will see in a second why. But importantly, it's just the last dimension. If it is the same and the first it's the same, then you know for a fact that the output is the same. So we unpacked it in tensor product form. We have the key value operations, and now we are basically unpacking that to the original definition of attention. Right? We have the softmax, and we are basically doing 2 things in parallel and merging them in the center, which is why you see those transpose operations. So we have T0 twice, which is the same set of tokens, or which is the same token, and when the tensor operations are presented in transpose, what we effectively do is evaluate it from left to right like normal again, rather than from right to left. So we go from T0 to WEWQ, and that's one set of equations, or like easy way to understand it at least, it's one set of equations, and WK sub WE times TO again is another set of equations, which makes sense if we look at it in the normal way of computing attention, because we first compute our key value and then our query value, and then merge the two with the dot product, correct? Which is basically exactly what we are doing over here, but just displayed more in a more concise fashion. Now, these operations again can be merged using the same principle as we used before, where everything on the right side, which is just everything, gets merged together, and we get this final equation 15. This is our second circuit. Right, and or these 2 equations combined are very, very important to us, equation 10 and equation 15, for that exact reason, because as you had mentioned, Aditya, the set of these 2 vector matrices, or like the set of these 2 matrices has the same vocabulary size, right? So it is the input that goes to the matrix, and the output has the same size as the vocabulary, which is important for eigen decomposition, but I don't think we're going to be able to get to that. So I was going to ask you all this question, but for the sake of time, I'm going to go a little bit faster. The three interesting things about this is that it is a much simpler recomposition of feed-forward inference because we don't have to do this entire recursive process that we had discussed earlier, and there is the attention is the only nonlinear operation. That's because softmax is the only nonlinear process, and finally the attention learns independently from the rest of the tensor equation because they are on different sides of the tensor equation. The one thing that we are missing, which I kind of skipped to, was the fact that we have W sub U all the way to W sub E and W sub Q transpose all the way to W sub E. And these matrices, when you combine them into a single matrix, because it's just a linear product, what ends up happening is that they have the exact same size. These chain tensor operations are circuits. They lie at the heart of the transformer architecture. So we're past 9 now. I'll finish the slide and yes.
Quick question before you finish.
Yes.
I'm confused on the difference between A and AH because aren't they kind of the same thing?
Oh.
Where like A was computed by like applying like the matrix representation of inputs to the actual softmax definition for a computed attention, while AH, from my understanding, it was done the same way.
Yeah, AH and AA are the same.
So
They're not different things. H just refers to the set of weights for the specific attention head.
Can you say that?
Sorry. So we have these separate attention heads, right? Multi-headed attention means
AH is the total attention, while A is for the single head attention.
opposite. So A is for a single. A is for A is for single head attention.
And A for all heads.
For specific head specifically.
A1 head. Okay.
Yeah, like A1 to A4.
Okay.
Can you go back 2 slides? I'm confused about something.
Which slide? Sorry.
2 slides back.
Okay.
There you go. Is there a reason why it changed from the last equation? It changes from T0 times W, the weights of the embedding, to then WQ2 times the weights of the embedding, because that would kind of change the meaning of it, so I'm kind of curious about it.
Sorry, what's
The last equation.
last equation?
It's T0 times the weights of the embedding,
Right.
multiplied by the weights of Q. But if you cross to the next slide, the equation is changed.
The equation. Oh, maybe I got that wrong then. 1 second.
So I'm not 100% sure which is which. Yeah, see there. Weights of the embedding is in another position compared to weights of Q. So
Okay. Oh, so these are completely separate equations. Equation 15 is the second one, right? Q is first, E is second, and then K and E. So Q, E, K, E, and it's. Oh yeah, you're right.
yeah.
Oh no.
Because if it's the first weight, then
Yes,
it's
yes.
something
You're-
like a variance matrix.
You're exactly correct. I'm sorry. I'm wrong. That is wrong. I'll correct that.
Yeah, okay, and then is there a follow-up question? Is there
Yes.
a way to interpret the weight of Q times the weights of K? Because if it has the first form, then that means it's more like a variance matrix. So I'm curious about that.
Q times K.
Yes, the weights of Q times the weights of K. Because if you notice, it has a matrix transposed by a matrix a vector transposed times a matrix
Right.
times a vector. That's like a variance matrix. That's
Okay.
has a
It's
similar.
a matrix. Like both are matrices.
Yeah.
It's vector times matrix times matrix. Right?
Mhm. Yeah.
So is it the same?
Yeah. No. No, I don't know how to phrase it. Sorry.
Okay. I'm sorry. I did not really fully understand either. But yeah, I'm confused.
Maybe
What is a
last
matrix? Sure. Yeah, we can talk later. Cool. Okay. Where were we? Over here. So we have the two circuits, the output value circuit and the query key circuit. The output value circuit determines how attending to a token affects logits, and query key specifically determines which tokens to attend to. So this circuit is basically a visualized version of it. We will talk a little bit more about how to interpret the circuits and why it is relevant next week. Thank you all for sticking around, and I hope to see you all soon.